Today we shall talk about the solution of an nth order linear differential equation. Nth order linear differential equation with constant coefficients. So why am I interested with this type of a differential equation? Let me come to this point. So first let us start with an example, then it will be easier to elaborate. Let us start with an example. So the standard form of this type of a differential equation is like this: a0 dnx dtn plus a1 dn minus 1x dtn minus 1 plus anx like this equal to 0. So where x is essentially a function of t and a1, a0, a1 up to an, these are constants like this. And obviously you know that dn dtn is the nth order derivative, dn minus 1 dtn minus 1 is n minus 1th order derivative, and so on. So let us take a particular case of this. Let us take a second order linear differential equation with constant coefficients. Let us take a particular second order linear differential equation like this: d2x dt2 plus 3 dx dt plus 2x equal to 0. Now, while solving this type of a differential equation, we often encounter in textbook that they say that there is a trial solution to this type of a differential equations, that we consider a trial solution to this type of differential equations, which is of the form x equal to e to the power mt. So where this m is a constant. Okay, so often we encounter this type of things in textbook, that there is a trial solution x equal to e to the power mt for this type of differential equation. Now here is the point, that this is entirely a wrong conception. So what I am trying to say, that this is not at all a trial solution. This type of a solution will exist for this type of a differential equation, and that can be ensured. Then this type of solution can be ensured through rigorous mathematics with operators. So if we do some rigorous mathematics on operators, we can see that this type of a solution can be ensured, and there is nothing with this trial solution. Now somebody can ask you that why are you taking such a trial solution, x equal to e to the power mt? How do you anticipate this type of a trial solution? So you have no answer. So this trial thing is simply nonsense. So there is nothing trial with this, and this type of a solution can be ensured for this type of a second order, or in general nth order linear differential equation with constant coefficient. So now let us see how we can ensure that. With this particular example, we will check how we can ensure that. Let us see. So let us start with our differential equation, that is d2x dt2 plus 3 dx dt plus 2x equal to 0. Now let us call this capital D to be the differential operator d dt. Then what is your second derivative d2 dt2? So for second derivative of x, you are basically applying this ddt operator twice on this x. That means you are operating this capital D twice on x, that gives you d2x, capital D to x. Okay, so if you consider capital D to be the differential operator d dt, so in that case you can just rewrite this equation as d2x plus 3dx plus 2x equal to 0, and which can further be written as d2 plus 3d plus 2 is operating on x and giving you 0. Now see what is this. So this is a second degree polynomial. Simply this is a second degree polynomial, which is often called a quadratic polynomial. So this is a second degree polynomial in operator D. So now if you replace a variable y in place of capital D, you will simply get this d2 plus 3d plus 2. This factor you can write this as y square plus 3y plus 2. So what is this? This is actually a second degree polynomial. Second degree polynomial in y, a variable y. And what fundamental theorem of algebra says that since it is a second degree polynomial in y, it will have two roots. So these two roots may be real or complex, same, distinct, etc., that we need not to bother about. But the main thing is that this second degree polynomial in y will have at least two roots. And due to the fact that this second degree polynomial will have at least two roots, we can write this second degree polynomial as, we can further break down it to first degree polynomials like this. In this particular case, we can write it like this: y plus 1 into y plus 2. So essentially in place of d you replaced y, and that gives you the thing like this. Again, in place of y, if you replace this capital D, so that will give you this d plus 1 into capital D plus 2. So essentially what you get, you get this one, that you started with a differential equation like this, and essentially you ended with this type of a differential, this type of a form. Now here you can see that these are first order polynomials. These are first order polynomials. These are first order polynomials in operator D. So in this equation now, these first order polynomial can commute with each other. So essentially from here we have two possibilities: either d plus 2, the operator d plus 2 when operating on x is giving you 0, or either the operator d plus 1 when operating on x giving you 0. So from this equation, these two possibilities, you get the solutions, the possible solutions of this equation. Possible solution of this equation are either d plus 2 equal operating on x is 0, or d plus 1 operating on x is giving you 0. So now you can say, what is this? Now this is very easy. What is d? D is d dt plus 2 into x, not into, is operating on x. So this is 0. That means this is dx dt plus 2x equal to 0. And what is this? This is similarly, this is d dt plus 1 operating on x is 0. and that means this is dx dt plus x equal to 0. Now you see that both these equations are first order linear differential equation with constant coefficient. So both these are first order linear differential equation with constant coefficient, and these first order linear differential equations with constant coefficients are very easy to solve. For example, if you take any first order linear differential equation like this, so you know how to solve it. It is very easy to solve. Simply you take dx by dx, you can write it as dx by x into this, and obviously a is non-zero. So if you integrate on both sides, so you will end up in getting ln x equal to minus b by a into t plus c. So ultimately you will get x equal to e to the power something, and this something is like minus b by a into t plus c, which is of the form k into e to the power mt, where m is some minus b by a, some terms like that will come here. So ultimately, so what is the crux of the thing is, if you solve this first order linear differential equation with constant coefficient, and which is very easy to solve, you will end up getting a solution which is of the form x equal to k into e to the power mt, where k and m are constants. So you just now try to look at the whole picture at a glance. So we started from this type of a linear differential equation. This type of a linear differential equation we started with, and we ended up in getting from this two differential equations like this, and another is dx dt plus x equal to 0. So and the whole process I just illustrated the whole process. So and from there you can guarantee that both of these differential equation will have a solution like k into e to the power mt. So disregarding the constant here, so you can guarantee that this differential equation, this original differential equation, will actually have a solution like x equal to e to the power mt. So you can ensure. So this is the whole procedure. The original equation can be further decomposed into these linear first order differential equations, from which you can just guarantee that this type of a solution will actually this type of a solution actually exist. So this is the general setup. So this is the setup for second degree polynomial. Now it's let us see for nth degree polynomial in short what will be the story. Let us just try to understand. So in case of a nth degree polynomial like this, suppose you have a nth degree not degree, nth order linear differential equation with constant coefficient. Suppose you have like this. Then a naught must be not equal to 0, and you can write this differential equation as just dividing by a naught. You can write this differential equation as this. So this is the general setup. Remember, this is the general setup. And if you take capital D to be the operator d dt, then you can write this equation as dnx plus here is a constant a1 by a naught into dn minus 1x plus dot 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 an by a naught x equal to 0, which you can further write like dn plus a1 by a naught dn minus 1 plus dot 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 plus n by a naught operating on x and giving you 0. So now if we consider that ai by a naught is bi for I equal to 1 to up to n, then this can be written as further dn plus b1 d n minus 1 plus dot 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 plus bn operating on x is equal to 0. So now this is a nth degree polynomial. So this is a nth degree or nth order polynomial. This is a nth order polynomial, and by fundamental theorem of algebra, this nth order polynomial will have n roots. These n roots, some roots may be same, all the roots may be distinct, roots may be real or complex, anything. We need not to bother about that, but it is guaranteed that this nth degree polynomial has at least n roots. So n roots, and because of that we can just decompose this nth degree polynomial in the operator d in first degree polynomials like this: d plus k1, d plus k2, like this, where k1 k2 are constants. Those constant may be real, may be complex, but we can decompose this into this. And now from here, so we have arrived at the end stage. From here we will get n set of equations like d plus k1 operating on x is giving you 0, d plus k2 operating on x giving you 0, like this. You will get n set of equations from here, and both all the n equations is a, you can recognize this, these n equations are first order linear differential equation with constant coefficient. And since these are first order linear differential equations with constant coefficient, we can guarantee that these will have a solution like x equal to some constant into e to the power mt. And from that we can just guarantee that our original differential equation, nth order linear differential equation with constant coefficient, our original this differential equation must have a solution like x equal to e to the power mt. So the whole thing is that this type of a solution, it is not a trial solution to this type of a differential equation. This type of a solution can be ensured by rigorous mathematics.